All right, so we have problem number 1 where there is a magnetic field and there is a loop in the magnetic field. The magnetic field is going into the page and the problem tells us that the magnetic field changes according to this formula. What we can tell from this formula is that it is an e to the negative power. So it's going to look something like this. And over time, we know that the magnetic field is going to decrease. Now, we develop an induced current when there's a changing magnetic field, and the induced current will always oppose the change. And since the magnetic field is decreasing, it'll want to create a magnetic field that will go into the page so that it counteracts that change. So the first thing we are going to do is, because we want the induced magnetic field to also go into the page, so that we're adding magnetic field to the one that's decreasing, then we want to figure out how to create a current that within this loop, we're always focused on the magnetic flux, which is the magnetic field within the loop. What direction would that need to go? So we're going to use the right-hand grip rule and see that in order for it to go into the page, we would have to have a current going in the clockwise direction. So clockwise, want magnetic field into page. So for this problem, we're going to use the right-hand rule. At each point of the circle, we're going to identify the direction that the current is going in, and you can, if it's clockwise, you can draw a tangent vector going in that direction at that specific point. So at the top, we're going to go straight to the right. I have a magnetic field pointing down. So based on the right-hand rule, I've got, this is my direction or my velocity of the charges. My force is going to go up. Here, again, I would have a current or velocity going down, which means that my force is going outward. So you're going to notice the pattern. The force is always pulling outward as you go around the circle. So this one is going to expand the loop. All right, now we're going to get into some actual calculation. So for problem number C, we're trying to determine the expression for the induced current in the loop. The induced current is voltage over resistance, and so we need to identify what the voltage or the EMF is by this system we have here. So we're going to go to our equation that EMF is negative d flux over dt, and we know that flux is B, well, let's call it N for the number of loops, even though we know that's 1, N be a cos theta. We also know that theta, which is your normal in relationship to the magnetic field, that theta is equal to 0, so cos 0 is also 1. And then the next thing we're going to do is identify what variable is changing. Obviously, they give us an equation for the magnetic field changing over time, and so we're going to take the derivative of B. A is a constant. So it is the area of the within the loop, and the area within the loop is pi r squared. That whole thing can get pulled out of the derivative. So negative pi r squared d dt of our B equation, B naught e to the negative gamma t. And then when we take the derivative of an E expression, we first take the expression itself exactly as is, and then we take the derivative of the function up here. And so the derivative of negative gamma t is negative gamma, and that makes these two negatives turn into a positive, and our EMF is going to be pi r squared b naught gamma e to the negative gamma t. I know that's kind of squeezed in there. That's not our answer though. It's asking us for the induced current. So kind of to save room, let me continue this equation over here. Current is EMF over R, which is equal to pi r, wrong r, little r squared, radius squared, b naught gamma e to the negative gamma t all over r. So that is our current for C. So for part D, determine the expression of the total amount of charge that passes a point in the loop during the time the field decreases from B naught to 0. This is an interesting equation. They are asking us for the amount of charge, and what we just calculated is the current. What we do know is that in our equation sheet, current is dq, the change in charge, over change in time. And so in order to identify the amount of charge, we are going to take our dq and bring it, the dt, to the other side so that we can integrate with respect to time. So I'm going to plug in my current equation. I've got a bunch of constants, so let me pull out all the constants. And then current, I, this is my exponent that I need to integrate. So I'm going to integrate both sides. For Q, we just want the full charge. So from 0 to the full charge, big Q, from the time the field decreases from B to 0, we can just call that 0 to infinity in terms of the limits of time. And so we get Q is equal to pi r squared b gamma r. The integral of E is e to the negative gamma t divided by negative gamma. And then obviously we're going to go from infinity to 0. We are then going to take our limit. So I've got pi r squared b gamma over, let's erase the gamma because that cancels out. And all we have in the denominator is r. And then the other thing we want to do is take the limit as e approaches negative infinity minus e approaches 0. That goes to 0. This goes to 1. And we have I forgot this negative. I'm going to pull that out because what I notice is that this negative 1, this right here is negative 1. It's going to turn that into a positive equation. So I've got pi r squared b over r. And I think I forgot to put the naught. So that's b naught. All right, that's D. How much energy is dissipated in the loop during the time the field decreases from B to time 0? In order to identify energy, we have to identify power. Power is a nice equation, especially since we have current and resistance. So let me try to squeeze E in up here. First of all, power is equal to dE dt, and we're trying to solve for energy dissipated. And we also know that power is equal to IV. So what we're going to do first is we are going to take our current equation, that is up here. Pi r squared b naught gamma e to the negative gamma t over r. And we are going to take our voltage equation, which is also, it's right here, pi r squared b naught gamma e to the negative gamma t. Basically the same thing, it just doesn't have the r. So all power is this numerator squared all over r. And then from there, we need to solve for dE, or solve for E. So I'm going to take dE is equal to, I'm going to pull out all the constants, square it over r. E also has to be squared, so negative 2 gamma t dt. Integrate both sides, and we're just going to go from 0 to infinity. And let me just clear out this space here so we don't need it. We have E is equal to pi r squared b naught gamma squared over r. The integration of this is e to the negative 2 gamma t over negative 2 gamma. And then we're going from infinity to 0. So we notice at least one of the gammas here. One of these gammas cancel out. And so I have E is equal to pi r squared b naught squared gamma over negative 2r. And then E goes from negative infinity to e to the 0. That makes this negative 1. And so, again, need to erase all this. But I've got E is equal to positive pi r squared b naught squared gamma all over 2r. And that looks like the correct answer from the answer key.